Hello and what's up to you all awesome and wonderful pre-matriculants. Welcome to a new slot. You guys are being promoted to the grade 12 slot. Well, that is a sign that we believe in you guys, so do make us proud. We're here to help you learn more and learn extra. My name is Abram and today we are with Emmanuel. Emmanuel, how are you?
I'm doing great, Abram, and once again, welcome back on Mindset, and we're going to have a look at Physical Sciences Grade 11, Paper 2 today, Abram.
Awesome. Well, to help you guys get ready, all you need to do is to get your notes on learn.mindset.co.za because we love you guys. I've already posted the notes for you guys on facebook.com/learnextra, so do check them out. It's the download and the viewing option. Lastly, follow us on Twitter at LearnExtra. During this show, I'll be also giving you some nice giveaways, a competition that I'd like you guys to get part of. But lastly, this show is proudly sponsored by M10 SA Foundation, and we're so grateful for all the resources and the help that they've been giving us. And also another thank you to the Department of Basic Education for endorsing this program. Over to you, sir. Let's begin.
Okay, thank you, Abram, once again. Now, today, learners, I'm so excited. Today, we're going to have a look at Paper 2, Physical Sciences, Grade 11, that you're going to write at the end of this year. And the aspects that you're going to have a look at is actually we're going to look at physical change, matter and materials, and we are also going to look at chemical systems, which is one of the sections that is set in your Paper 2 exam question. And I will say that there are some multiple choice questions that are there. Please just go there and attempt to try to answer those questions on your own. So we are going to have a look at content question, not the multiple choice ones, and we'll help each other through. If you've got questions, you can post them on Facebook, and Abram will alert me to say there are questions out there, and we'll be able to help you in there. And that's basically what we're going to have a look at today. Now let's just go and have a look at what is there. So we're going to look at matter and material, like I have said. So that's matter and materials, chemical systems, chemical change and chemical systems. And the question that we are going to have a look at first, we are going to look at the first question, which is a Boyle's law kind of question, or we are looking at gases rather in there. I'm just going to read it for you, and then we're going to see how we solve it up. Now, let's just have a look at it. They say now here, Ndiwuwo and Muraro plans to conduct a practical investigation. That's a practical investigation to determine the relationship between volume and pressure of an enclosed mass of a gas in a Boyle's law apparatus and a bicycle pump. They also plan that they will keep the temperature in the laboratory constant. Now, it's very important for us to know that. And they say, what will be the hypothesis for their practical investigation? In other words, when we talk about the hypothesis, we are just saying, just a guess of the relationship that is there between volume and pressure of an enclosed mass of a gas. Now, for those of you who may have done this experiment in the laboratory situation, you will realize that the hypothesis for this practical investigation, you will say here, because it's the relationship that we are seeking to find out, is that between what? Is that between volume and pressure. Now, the guess that we can say is, obviously they are related in some way. So when we change the other one will change. So let's just put this guess and say, we can say let's just say S volume, or rather, let's just use the pressure first. In that way, we can say as pressure of the enclosed mass increases, mass of gas rather increases so does the what? The volume. Or, that's a guess. Or we can say pressure is inversely proportional. Now, we must just get this straight here. So I said increase here, so we must say so does the volume. So remember, the relationship is an inverse relationship. So if we say as pressure of the enclosed mass of gas increase, we cannot say so does the volume. We can say the volume decreases. We can't say it increases. The volume what? Decreases rather. I'm sorry for that. So, or we can say the pressure of an enclosed mass of a gas is inversely proportional to the volume. That's right. So we can put it that way. In other words, we just need to find out the relationship between the what? Between the pressure and the volume. It's a wild guess. It's not a question, it's just a guess to say what is the likely relationship that we are going to have in there. I hope you get that. Now let's just go and look at the next question. And the next question reads as follows. They say, what will be their independent variable? Now, what will be their independent variable? In this practical investigation, the independent variable is actually our what? Is actually our pressure. Now we'll say pressure is our what? Is our independent variable. Now, the independent variable is basically that variable which you actually are changing, and then the dependent one is the one which you're observing. You will know to say, these are the changes. Now, the changes that you will note is the changes that you will note in the volume. So the volume becomes our what? The volume becomes our dependent variable. So I must just write here, the volume is our what? Is our dependent what? Dependent variable. Cool. Now let's move on. They say now, what is their controlled variable? I must emphasize that the controlled variable is that variable which you will ensure that is kept constant. It doesn't change. Now note that in this particular case, remember, it's an enclosed mass of a gas. Is the mass changing? No, the mass is not changing. So you will say the mass of the gas is your what? Is your controlled variable. The other very important thing that they said in the statement over there is that the temperature is kept constant. So it means that our temperature as well is our what? Is our controlled variable. So we can safely say here in the controlled variable, we can say the temperature let me just write it nicely over there. Yes, we said temperature is our what? Is our control variable, or we can say the amount of what? Of the gas. Or we can say the mass of the gas that will be accepted as well. So that's great. Now let's look at the question that follows now. So the question that follows in that very same vein, they say, now looking at the question that follows, they say, Ndibuo and Mulalo obtained the following results. Now these are the results that they obtained in this table here. So you have got the pressure here, you have got the volume. Now the pressure is in kilopascals, and the volume is in cubic centimeters. They can give you the volume as well in decimeter cube. That doesn't matter. So they say, use the results obtained to sketch a graph of relationship between pressure and volume. Now, in a Boyle's law experiment, now what is that relationship? In other words, the relationship between volume and pressure of an enclosed mass of a gas. What is that relationship? Now, we realized that in our hypothesis, we said, okay, inversely proportional. And remember, I said in our hypothesis, we may have said as well directly proportional, because we don't know. It's just a guess of establishing the two relationship. But we know for sure that in Boyle's law, the relationship is an inverse proportionality relationship. Now, let's just go down and sketch our graph in there. So let's just go down. So I'm going to say, let's just have a line in there. So we're going to have there, we have got our axis. So that's my axis there. And then here I'm going to put my pressure. So let me just get straight here. So that's your axis there. And then this is your pressure. That's your pressure. Remember, pressure is in what? In kilopascals. And then your volume is in cubic centimeters. Now, remember, this is a what? This is a volume versus what? Versus pressure. So we need to sketch. So when we have got an inverse proportionality relationship, we can put like this. So we can just have a line there, like that. So that's the relationship that they are going to find. That's how we can represent this relationship. So this is for an inverse proportionality relationship. And remember, if it was a direct proportionality relationship, we were going to have a straight line. Now, let's move on to the next question. They say, state in words the mathematical relationship between pressure and volume as observed in 1.3.1 above. Now, what have I just said? I said this represents a what? An inverse proportionality relationship. So just to state it in words, we can say volume of an enclosed mass of gas is what? Is inversely what? Proportional to the pressure exerted on it. That's our relationship. In other words, the volume of an enclosed mass of a gas is inversely proportional to the pressure exerted on it, like that. So that's the relationship that is shown by by what we find out from, that is represented by the graph, of course, and the results they obtain from the what? From the table. So now let's move on and look at the next question. So the next question that follows here, let's just look at that. They say, in question number 1.4, they say, determine the volume of air at a pressure of 200 kPa. Now we missed something here. They say, okay, let's look at this table. So we have got 200 kPa over there, and we have got X volume. Now, the question that they are saying here, they're saying, let's determine the pressure of air at a pressure of 200 and what? Of 200 kPa. So we are determining the volume of air at the pressure of 200 kPa. Now remember Boyle's law equation, and we can safely write it as P1 V1 is equals to P2 V2. Now let's move on and say, we are going to now look at it. So we are saying we have got pressure number 1 and volume number 1. That's equals to pressure number 2 multiplied by what? By volume number 2. Now, let's just we are going to look at this one. Let's just say I'm going to choose this and say that's my second set of results. So we'll put this pressure as P2, and then let me just choose this one here and say this is my first set of results. So I'm going to say that is 1. So simply I can go and substitute and say here for 1, I've got pressure is 450 And then, what's our volume in there? That's 10, so it's multiplied by 10. That's equals to, our pressure there in P2 is how much? Is 200. And that's multiplied by V2. We can safely say X. Let's just put X in there. Let's just put X in there and say that's X. I'll use a different color here and say that's X to get the point. So that's okay. And then let's use our calculator and find out how much our X is. How much did you find as your X? So if we go and use a calculator, we'll just say, oh, that's 450. 450 multiplied by 10 divide, or let's just first get the answer, and then let's just say go there and divide by 200. And equal sign there, and then we'll say how much. That's 22,5. Let's just go and write it there. So we're going to say that's 22,5 what? Remember here we're calculating the what? We're calculating the volume. So 22,5 cubic centimeters. That's the volume that we have got at 200 kPa. I hope you get that one and you enjoyed it. Now, quickly, we are just going to have a break, and then we are going to look at the questions that follows. Abraham, are there any questions that learners are posing?
I'll look at them and I'll tell you after the break.
Okay, no, that's wonderful.
If you have those questions, do send them through on our Facebook page. We'll see you after this. Welcome back, pre-matriculants. Now, there's this awesome competition that I think by now you should be knowing about. This is to help you guys. It is called a Be a Bright Spark competition. All you need to do is to buy yourself this official Safeways K53 Learners and Drivers Manual, or download the cool Android app, which is available from Google Play. Second thing you need to do, like our Facebook page, facebook.com/learnextra. Like the Facebook page of Safeways, facebook.com/Safeways K53. And lastly, fill in an entry form with all your details on our Facebook page under a tab which is called Win a Chevy Spark L. So guys, you could be the winner of 1 of 4 Chevy Spark L. All you need to do is to do the instructions that I told you guys. It's simple and it's easy, guys. The competition is closing on the 15th of November, and the winner will be announced live on the 23rd of November. For now, Emmanuel, I've got a question for you.
Okay. Bring it on.
Right. It's from I Am Young Calvin. How do we determine whether the variable is independent or dependent?
Okay. Now, Calvin, look here. To determine whether a variable is dependent or independent, you have to look at two things. One, you should look at if the variable which you have got control over, in other words, which you are changing, does the independent variable, the variable which you will observe and you will see some changes on it, that's the dependent variable. For an example, if let's just say I look at what I've got here in Boyle's law, and I've got a syringe and I've got a pressure gauge, and I push my syringe and observe the pressure that I've got first to say, okay, fine, I want a pressure of 150 and a push pressure of 150, and then after that, I look at my syringe and say, but the syringe here is at, let's just say, 50 cubic meters. It means that because the first one that I'm saying that I'm manipulating is my pressure, so that becomes your what? Your independent variable. And the other one that you say is being influenced here, you will say, okay, this one is my what? Is my dependent variable. So in essence, I'm saying that your independent variable, that one which you have got control over, which you are changing, and your dependent variable is that one which you observe and note. Whereas, just lastly, here, Calvin, The controlled one is that which you keep constant, that one which doesn't change. In our case, it was temperature. It was also the amount of the gas that we are given, the number of moles or the mass, whichever way you can put it. But that was the control. It doesn't change. So I think I have answered Calvin. Abraham, we can move on to the next
Thank you
question.
so much.
Now, let's just go and look at the next question. The next question look at chemical change. And let's just look on the board and see what does it entail. Let's look. So I'm just going to go. That's question number 2 there. They say the potential or the graph below shows a change. So the graph below shows a change in the potential energy for the reaction between calcium carbonate and hydrochloric acid. Now, this is the graph that we have got. So you can see there we have got potential energy in kilojoules, supposed to be in kilojoules per mole in there. So kilojoules per mole. And then that's the cost of the reaction. You can see there. And then let's move on. So they say, is the reaction endothermic or exothermic? Give a reason for the answer. We are saying that is this reaction endothermic or exothermic? And we should also provide a reason for this answer. So let's go back and look at this graph here. So look here. So here we have got reactants. So that's the part for reactants. And there we have got products. Now, once you have got a reaction profile wherein the energy of the reactants is higher than the energy of the product, that reaction there is an exothermic reaction. In other words, it liberates more energy than it absorbs. Now, we can safely answer this question now. What type of reaction is that one? That's a what? That's an exothermic reaction. Remember, if it was the other way around, we're going to say it's a what? It's an endothermic reaction. In this case, we say it's an exothermic reaction. And then the reason for that, we are saying that it releases more energy than it absorbs. So it releases more energy than it absorbs. So when more energy is released than absorbed, we know that that reaction is a what? Is an exothermic reaction. Now let's look at the next question. They say, use relevant values, that's A, B, and C, to write down the expression for each of the following. 2.2.1, energy of the activated complex. Now let's look back and say, let's look at that graph again. So energy of the activated complex, learners out there, is up there. That's where we have got energy of the activated complex. Now, what is an activated complex? That's a high energy unstable substance which is formed between the reactants and the products. High energy, it doesn't live for long, and that's the substance that we've got. So the energy that it has is represented in there. So which letter are we going to use? We're going to use A, isn't it? Yes, that's A. They said we should use A, B, and C, so we can use N. So we say that's A. Energy of the activated complex. Yes, that's A, and they gave you 1 mark for that. And then they say delta H for the forward reaction. Now, look here. Delta H for this reaction. So remember, delta H, how do we determine delta H? So we'll say delta H, let's just go down. Delta H is equals to heat of the final substance that we have got, or the product, minus the one of the what? Of the initial. I'm just showing you how to get that one. So what do we have for the final? In other words, for the product, what is it that we have got? There you are. We have got C. So we can safely say is C minus. What do we have for the reactants? We have got B. For the reactants, we have got B. So you can say C minus B. This represent what? This actually represent the delta H for the what? For the forward reaction. I hope you get that one straight. Now, let's just go and look at the next question. The next question reads as follows. They say, copy the graph and indicate the changes in the energy values if a catalyst was added. Now, how would the graph that we have got differ if we had a catalyst? Now, remember, learners out there, what is meant by a catalyst? A catalyst is a substance that speeds up the rate of reaction without undergoing a permanent change itself. There you are, a substance that speeds up the rate of reaction without undergoing a permanent change itself. That's a catalyst. Now, if we use it, what does it do? And what it does simply is it lowers what we call the activation energy. In other words, you will now have particles that were not qualifying to be products. Now, because the activation energy has been lowered, they can now qualify to be product. And it lowers that, and then you can have more particles now reacting. So let's just go back to our question and answer the question. They say, so we must indicate how is this going to be different. Now we can say, because the activation energy or energy of the activated complex has been lowered, let's just lower it and put it there. So I'm just going to draw a line and say, let's just put it somewhere here. And say, if it is lowered to there, so how will this graph look like? So I'm just going to try and say, okay, fine, energy of the reactants is going to be the same, but then on the, I'm just going to use the dotted line. So there you are, you see? So we are getting there. Note that the energy of the reactants and the products did not change. What changed? Only the energy of the what? Of the activated complex in there. A catalyst speeds up the rate of reaction by actually lowering the what? The activation what? The activation energy. I hope you get that as well. Now let's just move on and look at the question that follows. I hope there are no questions, Abraham, in there. So let's just move on and look at the question that follows. So the question that follows, which is question number 3, it reads as follows. This is an interesting question, I must say. They say, iron is usually extracted from hematite. Iron ore is mixed with limestone and coke in the blast furnace. Now, this is a chemical system kind of question. So, they say to produce metal, the following incomplete word equation describe the extraction process. So, we have got the reaction here. So, we have got, they say the first reaction, we have got coke. So, that's coke. Plus oxygen giving us gas X, and then you've got gas X mixed again with coke giving us gas Y. And here we've got iron 3 oxide plus gas Y giving us iron plus gas X. So note that the coke that we're talking about there, it may be different to the coke that we may be thinking about. You'll get it as we go on. Okay, now they say, name gas X and Y. So what is gas X and what is gas Y? So I'm just going to write X and I'm just going to put Y. And we'll go back and have a look at that. So the first thing here, they say, coke plus oxygen to give us gas X. Now what is coke? Coke is carbon. Carbon is, can I say carbon is coke? But let's just stick to this. Coke is carbon, and that's just C there. So that's C, that's carbon plus oxygen. So what gas are we going to have? The gas that we are going to have, learners out there, is carbon dioxide. So which gas is this one? Is X. So our X is actually what? Carbon dioxide. That's CO2 gas. And let's look at the other one now here. They say gas X, which is carbon dioxide plus coke again. So this gas. So plus coke again. Our coke is solid there. So when you add the two, you get another gas. This gas here is carbon monoxide gas. Oh, yes, guess what? Guess why? It's carbon monoxide. Carbon monoxide gas. They say now, quickly, write a balanced chemical equation for reaction C. Let's quickly go back and look at reaction C. Reaction C, there we've got iron-free oxide plus gas Y to give us iron plus gas X. So we can say iron-free. So it's iron-free oxide. So that's what we're going to have. And that's solid plus. They are saying it is mixed with, guess what? Gas Y, so which is carbon monoxide gas. And that gives us what? Iron, which is Fe, solid plus. Gas X. Which gas is gas X? Yes, you get it right. That's carbon what? Carbon dioxide. That's CO2 gas. That's what we have got. And let's just quickly go and look at question number 3.3. They say, what role does gas Y play in the blast furnace? Let's just go back a little bit, and I just want to check to ensure that at least our reaction equation is balanced. Let's just check that is balanced, because they said balanced H. We should have ensured that it is balanced. Let's check this one. So we have got how many iron this side? We have got 2. That side we have got how many? We have got 1. So let's put 2 over there. And then how many, let's just move on and say, how many oxygen do we have on this side? We have got 3 there. We have got 1 over there. So we add that is actually how much? So you are going to get it. How much is it? So we actually have 3 here. And we have got 2. Let me just check how much, how are we going to actually balance it without it wasting our precious time. Let's just get this out and that. So we can just put 2 over there, and voila, that's balanced, isn't it? So if we put 2 here, that should be balanced. Let's just check that. So we have got 3 here, plus that one is 2. No, it shouldn't be balanced, because here we've got 3, we've got 1. Now, we'll have to get back to that one. We'll have to get back to that one, because that one doesn't balance. But maybe quickly we can just get it. So it's 2 here, 2 that side. Iron is balanced. So oxygen, we have got 3 here, and then 1 there. So that makes it 4. This other side, we have got 2. Let's just put 2 there and say, if we have got 2, so it's 4 that side. And how much do we have this side? We have got 4. We can put 2 here. Oh, voila, carbon is balanced. So carbon is balanced, oxygen is balanced, and iron is balanced. So remember, iron is Fe, not just F. So great, we have got our reaction equation balanced, and I so believe that you got that one right. That's the balanced reaction that we have got for that particular reaction. Unfortunately, we couldn't get enough time to actually complete this, but after the break, we'll just spend a minute or so and just go through the last part. Abraham, any questions from our learners out there?
Awesome, Sir. I do have some questions. After the break, we'll tackle them. And a big shout out to all the mindsetters that are watching, especially Junior Maduna, who's texting us and saying he's enjoying the show. A big shout out to you. We'll see you guys after this break. Welcome back, Mindsetters. Now, on the K53 competition that we're running, we always want your views. Each and every week, we've got info posts that we're posting on our Safeways page, which is facebook.com/SafewaysK53. We'd like to get your views. And this week's topic is, it's a simple question. Are you or one of your family members guilty of texting and driving, and how do you feel about that? Maybe you say have been a victim and guilty of this. Have you texted and driving and drove at the same time?
Abraham, don't put me on the spot.
Well, it's clear. It's clear. Well, my mindset is if you or any of your family members, you have seen somebody texting and driving, let us know about that. How do you feel about that? Do you feel it's a dangerous thing? And what are your views based on that? I'll post the question on our Safe Ways page and also in Mindset. Let us know what you guys think about that topic. We'll watch out for the comment with information, a video that will be posted tomorrow or later on this week. Back to you, sir. I won't ask you anything related to that.
I must say, Abraham, that's very dangerous, and it's something that I would advise that we don't do that. Don't text while driving because it's two-way dangerous. So let's just get back to our questions and just go through them once again. So the question that we were answering was question number 3, and we are just going to conclude this question, but we'll come back to it later on to just clarify some of things. They say, question number 3.3, what role does gas X play in the blast furnace? So which gas are we talking about here? So we are talking about gas X. So let's just get this right here. So we are talking about gas X. Which gas? Gas X, and that's gas X, which is carbon dioxide. So I think it should have said gas, or it's gas Y. Rather, gas Y play in the blast furnace. I was not getting it right. So gas Y is carbon monoxide. And what it does here, if you look at this reaction equation here, so as gas Y reacts with iron oxide, it actually reduces iron oxide to give us what? To give us iron. So we can safely say we can say gas Y, which is what? Which is carbon monoxide, reduces iron oxide to iron. So we can say, not write it in so we can say 2 Fe. So 2 Fe. So that's what it does. Or we can say is a reducing agent. We can say that. We can safely say that because it reduces iron free in iron oxide into iron metal, that is Fe. Let's just add that. That will be solid. So they say the next question, they say, very high temperatures are required to melt the ore. How is this achieved? So we've got very high temperatures because obviously we have to melt the iron in there. They say, how is this achieved in the modern blast furnace? How do we achieve this? So what we do is that we blow air from, let me just write it clearly. This is not clear. I just have to put it very clear so that at least we can all see. So we can say air is blown from the bottom part of the what? The bottom part of the furnace. So that's how we actually achieve the high temperatures that are required. So that's how we actually achieve those temperatures. Now the last question, this question number 3, they say, why is limestone added to the reaction mixture? Why is limestone added to this reaction mixture? Now, what is limestone? Limestone is actually calcium carbonate. So calcium carbonate is added in there, and what happens is that calcium carbonate decomposes into calcium oxide and carbon dioxide. When it does so, the calcium oxide actually remove the impurities such as silicon dioxide. In other words, we don't want the impurities in our ion that we are producing, so we put in calcium carbonate. As it decomposes, the calcium oxide removes the silicon dioxide. So I'm just going to write it. So calcium or limestone, or we can say calcium what? That's calcium. Let's just write it nicely there. So we say limestone is calcium carbonate. Decomposes to give calcium oxide, which we rather say which aid aid in removing impurities such as silicon dioxide. So calcium carbonate, which is our limestone, actually does that to ensure that at least the ion that we have got at the end is as pure as it can possibly get. I wanted to tell Abraham something, but I will tell him at the end, towards the end, so that at least he understands. But it was going to look at the importance or how iron has been used in some long time ago. Abraham, Eiffel Tower, which is actually one of the towers in France, I'm told that it has been built using around 7,300 tons of iron, which is actually what we are talking about here. Just imagine, when I was actually calculating it, I realized that, we are talking about huge amount of iron that I'm like, if you compare it, it will just be, I'm like, so many cars being produced by that iron. But that's just something that I wanted to tell you.
I have something to tell you.
Yeah.
Well, it's also related to this. There's a previous question, the equation that you were struggling to balance there.
Oh, yes.
I have the right equation.
Okay, no, that's great. Let's just go back and just check how it was supposed to be balanced there, Abraham.
I was sweating trying to figure it out.
This one, yes, let's just get it back.
The correct one is Fe.
Fe, yeah.
203.
Yes.
Plus.
Yes.
3CO.
Oh, 3CO, yes. Let's just get it right here. We didn't get this.
You missed it right there.
We missed it right here. So, that's some of the things which happens when you are rushing, So this 3CO, that's our carbon monoxide gas in there. And then?
And I think the rest should be correct. 2Fe plus 3CO2. So
we should put a 3 here because the carbon will not be balanced if it's just to the, so we'll say plus 3CO what? We say CO2. So remember, that's gas. Thank you to the person who actually helped us in there.
You're
now
welcome.
Let's just go and look at the next question, and that will be question number, we're just going to have a look at the next question, which is question number 4. Now quickly, question number 4 reads as follows. They say, in each case, compare the two. They say we've got, in each case, compare the two given substances with each other in terms of boiling point. Each time, show which substance should have the highest, so they say highest boiling point, and give reason or give a reason for your choice. Now, let's just have a look at this. So we have got here that substance and that substance. We have got hydrogen fluoride and also methyl fluoride in there. So let's just look at how are we going to determine that. So this substance here, I said methyl fluoride, it should, we can safely say is fluoromethane. Fluoromethane. So we've got fluoromethane, and we also have what? Hydrogen fluoride. Which one has the what? Has the higher boiling point? So now let's determine. So this one here, to determine the boiling point, learners out there, just remember, we need to understand the concept of intermolecular forces. The substance with stronger intermolecular force will have higher boiling and melting points. And in other words, substance with intermolecular force such as hydrogen bonds. Remember, hydrogen bonds are intermolecular forces which are much stronger than the van der Waals forces. So substance with hydrogen bonds will have higher melting and boiling point. And that's very important to note. And that on its own determines the physical properties. Let's just go back and look at the ones that we are given. So these two substances here we have got hydrogen bonds, and then, in other words, here we have got hydrogen bonds, and here we'll have dipole. So because these intermolecular forces, these ones are weaker than the hydrogen bonds, so we can say hydrogen fluoride will have what? A higher boiling point. And then, why is that? We can safely say because it has what? We can say it has stronger intermolecular forces, which are in this case what? Hydrogen bonds, like I have said. I have indicated there, that's hydrogen bonds, whereas the other one is dipole. Now let's just go down and say, now between fluoromethane and bromomethane, which one will have a higher boiling point? Now, if we look at it, we've got fluorine here, we have got bromide here. Now, which one has a bigger surface area between the two? Both of them, yes, they will have dipole in both of them. So dipole, I say dipole there, yes. So that's dipole. And if we are saying that both of them have got dipole, but look here, as we check in the, let me just get this line out of here. So the surface area of bromide is actually greater than the surface area of fluorine. So in essence, the stronger intermolecular force, the stronger dipole will be in bromomethane as compared to in fluoromethane. So bromomethane will have a higher boiling point. So in other words, we can say, let's just get that straight. So we say CH3Br will have what? Higher boiling point. The reason is that bromide has what? Has I can say greater. Let's put that way. Greater surface area than what? Than fluoride, because the atom is bigger, and hence that will lead to what? That will lead to us having a stronger intermolecular forces in bromomethane. And then the last one here, they say fluoromethane compared to ethane. Now, comparing the two here, look here. The chain in this one is actually longer than the chain over there. The longer the chain, the stronger the intermolecular force is. Now, which one has a longer chain? The one which has longer chain is actually fluoroethane, or 1-fluoroethane. Now, because it has stronger intermolecular force, it will then have a higher boiling point. Now, let's just put that down. So we are saying that CH3, CH2F will have a what? Will have a higher boiling point. It has longer chain. In other words, it can we say longer chain, or we can say the molecule is we can put that way and say the molecule has greater, I can put that way as well, greater surface what? Surface area. Because it's what? Because it's longer, it's a longer what? It's a longer molecule. It's a longer molecule. That's it. So we can put it that way. We are safe if we put it that way. So note that the length of the chain determine the strength of the intermolecular forces as well. Same intermolecular forces, but if the chain is longer, the one with a longer chain will actually have much stronger intermolecular force, which will determine the boiling point, the melting point, the viscosity, and a whole number of physical properties. Now let's look at the next question that follows. So that will be question number 5. So this question number 5. So they say vinegar, which is used in our homes, is a dilute acetic acid. A sample of vinegar has the following percentage composition. They give you 39.9% of carbon, 6.7% of hydrogen, and 53.4% of what? Of oxygen. And they say determine the empirical formula in there. Now, to determine the empirical formula, we just assume that you have got what? You are given 100-gram sample. So you say, I'm given 100 gram of what? Of acetic acid. So if you are given 100 gram, it means that for carbon you will have what? You will have the mass of carbon will be 39.9. So we change those percentages into what? Into mass, and then the one for hydrogen will
Emmanuel.
be...
Because of time, we're really running out of time. I think we might just have to post the answer to the mind-sitters. Time is really against us. It's always our enemy.
Sure.
But thank you so much for all the work, and thank you. Thanks to you guys for watching. We really appreciate it. Because of time, guys, do check out all the notes and trying to do the workings. But a big thank you to our sponsor, MTN SA Foundation, for making this show possible for us, as well as the Department of Basic Education for empowering us. We really appreciate it, and we believe in you guys. All the best in all you do. Keep on believing in yourselves, because we believe in you. From us and the rest of the team, peace.